today I'm going to try and summarize some of the key results that we've been working on for almost 4 years now, maybe 3.5. And this is a project that was originally started when I was back at NREL. I've been working closely with Yashin on this. And so I'll jump ahead here. I want to acknowledge all the people that contributed on this. So here are my collaborators at NREL, University of Minnesota, and UCSB in California. So yeah, this was really a team effort because this was really pulling together things from multiple angles, from the theoretical side of things as well as the hardware and experimental side of things. So I think we needed to have that cross-cutting expertise to pull this off. Okay, so I'm not going to dwell on this because I think we've seen this image too many times probably at this point. And so actually what I'll do is I'll just say very quickly that we're in the presentation, we're going to study some of the properties of both of these control types, the conventional following and these new forming controllers that we're looking at from both a modeling standpoint as well as experimentally. Okay, so here's a snapshot of these controllers. So on the left-hand side, the grid following control is what really makes it that, at least in the way I'm looking at things, is it has this phase lock loop. So that should catch your eye here. And then the other two controllers that are most commonly used, aside from virtual synchronous machines, is droop control. And then we've been looking at this virtual oscillator control in particular in our project. And so these two grid forming controllers, they at first look very different from each other. The droop control has this very well-known frequency versus power and voltage versus reactive power trade-offs that everyone knows and loves. And then you look at this thing, which looks very different and strange. But it turns out that when we first started doing this, we did some legwork to analyze the dynamics of this new oscillator type controller. And if you look at its quasi-steady state behavior, it has droop-like functions embedded inside of it. So it is a lot like a nonlinear droop controller. And we did that so that people wouldn't be so scared of it when they saw it. And it really shows you that there is an underlying functionality that these grid forming controllers have. It's these droop-like functions that allows them to function. Okay, so there's two pieces I wanted to talk about in the presentation today. The first one was actually kind of a side point for our project. We originally wanted to analyze stability, and we actually did a lot of work on small signal stability, kind of a precursor of what Duncan was expanding upon and looking at. But before we could even look at that, we had to address this issue we call the modeling complexity issue. And even though it began as a side kind of focus of the project, we realized it was super important. And then the other part is the experiments that this is culminated into. Okay, so let's look at this modeling complexity issue. So what is this? So you have synchronous generators that are quite large, hundreds of MVA, and you go and buy an N-phase microinverter at 300 watts. So we have orders of magnitude, size, and difference. And of course, in real systems, there's going to be a split between bulk megawatt scale inverters and distribution level. But we could be looking at talking about bulk systems having thousands of generators to potentially hundreds of thousands of converters or even millions, depending on the size of the system and how prevalent, especially microinverters, become on systems. So here's just an example. Actually, these numbers are probably getting a little old now. They might be they're probably even higher now. So in Hawaii, they've really taken to using the PV microinverters. So in Oahu, there's roughly 950,000 people. And basically, when I grabbed these numbers from the Spectrum article, there's 800,000 N-phase microinverters. So there's almost as many N-phase microinverters than human beings there. And then I talked to another good friend of mine who knows a lot about the total number of inverters with all the manufacturers. And he told me that if you add up everything, there are more inverters than human beings in this place. So it's a very interesting little motivational example of why we have to deal with this modeling complexity issue. We can't simulate hundreds of thousands of things and actually hope to get something useful out of it. So what we are doing is aggregation. So we're working on this framework where, let's say you have a collection of converters that are all sitting in a pocket near each other in a part of the grid. And we want to formulate an aggregated equivalent that is much, much lower complexity. In our case, it's actually, this has the complexity of a single inverter, actually. And once you have an aggregated equivalent, let's say that this captures the behavior of 10,000 inverters, then you can actually plug that into a bulk system and do something at a transmission level and see how things interact with one another. Okay, so let's peer under the hood here. So on the left-hand side, I have drawn here like a cartoon of what I call a scalable inverter model. And the idea here is, let's suppose that you have a piece of hardware that is sitting in your lab, or it's a specific inverter. Let's say you have this specific model from a manufacturer, and you know all of the control parameters and the filter elements on it. And let's say it's a 10 kilowatt three-phase inverter, and you say, I want to know what this model, or how I can model this 10 kilowatt inverter if it was hypothetically 100 megawatts or 1 gigawatt in size, and I want its behavior to be exactly the same, just scaled up in power levels. And so this is the drawing here, where you can see there's two knobs we have. There's a power scaling knob, which I call this kappa P in orange, and then there is the voltage scaling, which you can also adjust the voltage rating of that converter. So those are the two knobs we have that you can impose onto a baseline model that, let's say, you have when you have already characterized. And so the way that works is on the output physical elements. So there's inductors and capacitors. You can scale them just as I've shown here, and that is one way that's how to transform the original parameters to this scaled up version. And it's not completely arbitrary. It actually has some level of, justification if you look at if you were to physically take a 10 kilowatt inverter and then make a 1 megawatt version of it, you might get something similar to it. So you actually get a consistent voltage drop across the filter, and this also gives you a consistent distortion that's produced from the switching. And actually, as Duncan hinted, this is actually just another way of doing per unitization. You can kind of think of it as you can per unitize it in one base and then scale it back up to another one. You get the same thing. Okay, of course, there's also the control loops. So this is all the digital side of things, and you have to do both. I don't show it here, but all the proportional and integral gains that reside within the current control loop and the phase lock loop, you have to scale those too. And the objective here and what we obtain is that if you have your original baseline model, say your 10 kilowatt inverter and your megawatt one, you subject them to a transient, they both have the exact same shape. It's just one is a scaled version of the other. Okay, so that is just one single inverter. Okay, so here we have this scalable inverter. These denote, those are the two knobs that we have associated with the single unit. So you can make this larger or smaller. And actually these scaling laws that I showed on the previous slide, I showed you how it looks for a grid following type with a PLL. But you can do this with a Droop controller, a virtual oscillator controller, and you can get scalable versions for either of them or any of them. Okay, so now you take n instances of these things. So let's say you're looking at a system that has 10,000 inverters, and they're all scaled versions of each other. And so they each maybe have a different rating associated with them. I actually talked to someone at a manufacturer who makes large three-phase inverters, and he said that these scaling laws are actually very similar to how they scale their controllers. So they recycle their per unitized controllers in 100 kilowatt versions, 500 kilowatt versions, and megawatt scale versions. So it's very much in line with that, which brought me comfort to know that this does align with that. And then once you have that, what we show here is, and I'm skipping all the math here, is that you do get this aggregated equivalent, and it's very intuitive. The power scaling of the aggregated equivalent is just the sum of the power scalings in the individual units. In other words, it has the power rating of the cumulative sum of all of them. The voltage is unchanged because they are all connected together electrically. And then we get an equivalent output current that I denote with this superscript E. And then if you do all the math, which would just be slides full of nonlinear differential equations, which I don't want to subject you all to, you can show that all the math goes through. The equivalent output current of that aggregated equivalent is exactly equal to the net current produced by all of the individual units. And what's really cool here is that the aggregated equivalent has the same structure of a single inverter. So it doesn't look like some weird new dynamical system that has no connection to physical reality. It looks like another inverter too, it's just scaled up. Okay, so here are the references below where we do all the detailed differential equations in algebra and show how this works out. Okay, so this is actually something new and recent. This is actually snapshots from a conference paper at PVSE that's under review. And everything I just showed here is assuming ideal DC sides. So we're wanting to now continue this line of aggregation work where now you include the DC side dynamics. And this is important when you have photovoltaics especially. So here is just a drawing of essentially the same thing. This is just the same inverter model. You can use the same scalings just as I showed. And if you have n copies of these, let's say this is a utility scale PV plant with, let's say 20, 40, 50, 100 three-phase inverters, then you can model them as this aggregate equivalent. And in this very simple case, if you have n of them and they're all the same, then here is this scaling factor n that shows up. And this is, again, same line of reasoning that allows you to get the aggregated equivalent. Now, one thing I do want to highlight here is we do include the MPPT dynamics. We have the behavior of the PV model on the input side. And we have the DC link voltage regulation that we're doing here also for MPPT. So it includes the full set of dynamics to have a functional PV inverter. Okay, so just it maybe seems very abstract and unclear how this connects to real stuff. So we built things so that we can convince people that this actually does connect to how things behave. So here is an experiment that we built at NREL. So we had 3 of these inverters, and we programmed them with both grid following conventional controls and also this oscillator type control. And this is the experiment, and then we compare that to a simulation where we just simulate the differential equations of the aggregated equivalent, and we just overlay those on top of each other. Okay, so here is the experiment with the grid following controls with a PLL, and you can see that we get a good match for the total current coming out from the model in the experiment. And then sometimes it's easier to see things in the DQ domain, so if you run these measurements through some transformations, you can get these waveforms here, but they're the same thing. And so that was a very nice result. And then we also did this with the grid forming controls. And here we actually introduced some heterogeneity. So one of the inverters is half the size of the other 2. There's 3 of them. And again, here we get a good match. So here are the individual currents. Here's the total current, both simulated and measured, and we get a good match on those. So this allows us to, again, if you go back to a big system, you can take pockets of large numbers of converters and model them with some reasonable confidence that you're capturing that behavior. All right, here's the recent result that's still under review. This is actually with the PV inverters. They all have their own MPPT, perturb and observes. They're all doing their independent thing. They're not synchronized, and it was actually very nice to see that the aggregation still works quite well then also. Okay, so that's the modeling complexity issue, and again, I don't have time to cover this, but we use that to do some small signal stability analysis on systems, and so we have a bunch of other papers on that. Okay, so the other thing I wanted to do here is highlight what we built. These are, you're lucky people in the audience today get to see these because these aren't published yet. So this is something that we're working on getting out. And in this project here, we partnered up with SunPower and their microinverter team, and we were able to convince them to reprogram the firmware on their inverters with these virtual oscillators. And we went ahead and built an experiment. And microinverters are super convenient for these experiments when you have complexity, because you can just have lots of them in a small place, and you can get just really fascinating experiments put together without having to have a huge infrastructure to make that happen. Okay, so the heterogeneity is a key issue, and making sure that all of these things work well together. So the experiment has 10 grid forming units, 10 grid following units. They form a 100% power electronics mini grid. And each of these represents a pocket of 5 inverters, where the various flavors that each of them are is highlighted here in blue and green. And then we put impedances between them to simulate or emulate what would happen if they have physical lines separating them. And then, of course, there's loads on the system. We also threw in a capacitor to capture what would happen if you have a distribution system with some capacitor banks on them. So reactive power is a major issue that you have to be careful with on these. Okay, so let's take a closer look at what this thing actually looks like. So here are, this that I'm highlighting here is a pocket of 5 microinverters. Here's another 5. So you can see there's 4 groups of 5. And each batch of 5, or actually one half of the system is forming, the other half of the system is following. And then here is the DC side to power those up, and here are the load banks. So it's just a resistive load bank. Okay, delving a little further into physically what this looks like. So again, this was the convenience of working with microinverters. So this is just sitting conveniently in 2 racks. These silvery kind of thin boxes are the microinverters. So there's batches of 5 in each one of these. Here are the magnetics that capture the inductive lines that separate them all. And then we also even have the load bank sitting in here that we can flip switches on one side of this cabinet to impose load steps. The other important aspect of this too is it was important to show people that, of course, if I have a custom-built inverter that me and my collaborators built from scratch, and we put some new crazy controller on it, that's only somewhat convincing. But actually working with a commercial manufacturer and doing it without any hardware changes, it's purely just software firmware changes, is I think a big step to show that these things can be done. Okay, so this is actually a really complex experiment that was put together. It's actually Gabsu is in the audience right there. He's the superhero here. That he would be Superman if I had a slide with him. But yeah, he actually did a lot of the heavy lifting here of getting this experiment up and running. And here's just a picture of how everything works. So we start out completely from black start, and it's a staged way of building the system up. So to get the system up and running, we have to turn on the grid forming units. We do have a slow power line communication that is used only for on-off signals. So aside from that, there's really nothing else that the power line communication is used for. Actually, I do have to be careful. There is the grid following ones that can track power set points. You can set those. But the grid forming ones act as like they almost cohesively, they act like a slack bus on the system. Okay, so each of these arrows here are just showing load steps and how we gradually energize the system. And here are power steps coming from the grid following units. We also, here's a step on the capacitive bank when we throw that onto the system. And then eventually we arrive at the full scale operating microgrid. So I'll just zero in on a few of these key spots. So I'll do, it would take a while to work through every step, and it would just be a bunch of waveforms. So I'll do something at the beginning, I'll do something in the middle, and then I'll show you something at the end. and then you'll have to just trust me that we did all the stuff in the middle. Okay, so here's black start. Here's the really probably the toughest part actually, and the part that is most sensitive when you're doing this. So here we're turning on 5 microinverters. So this current here that's in yellow is, I call it I inverter 1. That is what's flowing through this branch here that has L1. So it has the cumulative current that's coming out of, oh, I'm sorry, that's the blue one. That's I line 1, and I inverter 1 is the first converter in this batch of 5. So you can see when you turn on that first one, it has to carry the full brunt of the load. And then as the other ones turn on, then they share the burden of that evenly. So we have to start out with a fairly light load on the system. And this highlights that, when you do black start and you have a heavy load, that's a really tough situation. So anyway, that's still work to be done. Okay, so they share the power. And then once we gradually introduce additional inverters on the system, we reach this point where we have 10 of them operating. So it'll be 50% following, 50% forming, and then we'll impose a sizable load step on the system and see how they behave. So just before I show you the waveforms, the way the following units work, so if, let's say these were PV, they would just be injecting the power that is incoming from their PV module and their input. These were actually controlled with a power supply at their input. So they're just following a set point, and they're holding a rock solid power output as if it was just constant irradiance. And so when you have a load step, who picks it up? It's the grid forming units. They act like a slack bus on the system, except it's distributed amongst those units. So let's take a look at that. All right, so the load voltage is not very interesting. The load current, you can see here that when we flip that switch, we have almost a doubling in the size of the load. And then I line 1 is what's coming out of the grid forming units. You can see that they are the ones that pick up that extra burden, whereas the grid following units, which are sitting over here, we have a current sensor on this line number 3, they ignore that. So they just continue pumping in the same amount of power. Okay, and then the very last thing is, actually the hard part of this is just getting up and running. And the bigger you make the system, the more robust and bulletproof it becomes. And so once you're here, you can pretty much throw whatever you want at it and it survives. And so this is the full system up and running. This is these on-off commands for the various units are happening in the sequential pinging and turning on the last 5 microinverters. And you can see that, that when you do that, there is this sharing behavior. And the load doesn't really know that. The load is just consuming a constant amount of current. Okay, I think that concludes my talk, so I'll be happy to take questions.
About the multi-aggregation part, so I just wonder, so how you, several questions actually. So if we consider the same inverter vendor or connecting the same location, seems actually pretty straightforward, right? Scale up. But when you consider they are over geographically dispersed, and so how do you, aggregate the model of that situation?
Yeah.
And I think the second one question is specifically about the PV. And so how you consider the different inverters if they operate at different setting points? Because on the DC side, it's totally different, right? The impedance and it's different. So how do you consider that in the aggregated model?
Yeah, that's pointing to some very important issues that was actually on our minds when we started out doing this. And the results I showed were for the simplistic case where everything is just copies or scaled versions of each other. And that's where the math works out most cleanly. But we do have a couple other sets of results I didn't have time to show. One of them is, we call it network cognizant aggregation. So if you have impedances between a system, you can make clusters where based on electrical distance from each other, and you can aggregate those and you'll get something that's approximate. It's not exact, but it's really close. And so we have a paper under review on that. And so there are ways to address that. So that's the network aspect. The other one is the heterogeneity of the inverters themselves, which is not only the physical elements on the output, the filtering elements, but also the controls. And so I have another paper that we just submitted also under review where we were looking at that. And again, you get something that's approximate, but when you compare the total sum current from all the individual units, heterogeneous, versus this approximate model that we had to use some assumptions to obtain, they're almost exactly on top of each other. And it really boils down to looking at the aggregated current command that they're all tracking, and you can play some tricks to get a model that does a reasonably good job of capturing that. So anyway, there are results that will be trickling out here hopefully over the next 6 months to 1 year.
Brett?
Yeah.
Great. Thanks a lot. So I have a couple of questions about the black start stuff, which is super cool. And one is the load, the kinds of loads you're using. Could you talk a little bit more about what the load emulator is doing, and if you think you get different results if you emulated different kinds of loads?
Yeah, so this is where Gabsu could probably just tell us how difficult this was. The black start is tough because, okay, let me say first the load. The load was just a resistive load bank, and we just have switches that throw resistors on there. So it's a very simple load. I have done in the past other experiments with nonlinear loads and inductive and capacitive loads, and things still seem to work fine. But what makes this challenging is whenever the system is de-energized, it's not as if these inverters have switches that are separating them. They're all connected to the system. It's just that their power electronics has all the semiconductors are acting like open switches. Now that means that although the switch part of the power stage is open circuited, the filter elements are there. So each one of these inverters has inductors and capacitors hanging out on their outputs just on the system. So when you're this lonesome inverter that has to turn on first and you're looking out, you see a bunch of inductive lines, a capacitor here, and a bunch of L's and C's on all the filters, and it's a pretty heavy reactive load. And so we actually had to be very careful so that when that first unit turns on, it's not overloaded by the reactive power load across the system. And a big bulk of it was all the filtering elements on the outputs of the inverters. So anyway, that was a very contrived and controlled thing that we had to do with a very light load. But yeah, so there's lots of work yet to be done on how to do this gracefully.
Brian, Scott again. Quick question. One of the challenges we commonly have with inverters is energizing transformers and such forth, including the DC offsets associated with it. Is there any ongoing research that you could point us to or point the industry to alleviate these problems?
So I don't have a good awareness on work yet for grid forming that is tackling this magnetizing issue, and even we ourselves haven't gotten that far yet. My feeling though is that if you have a grid forming controller that has a voltage command and you have inner loops that act on that voltage command, which includes a current loop, you would probably have to add some limits on that innermost current loop to have a very controlled current as you're magnetizing. But that's a very open question still.
A quick comment on that. And there might be national lab people working on this specific problem. There was a utility that used an LM6000 as a black start, but it was leveraging the substation 280 MVA transformer and that swamped out the inrush, swamped out the heatless combustion turbine. I'm pretty sure the question went to a national lab to help this particular California utility, so I might ask around. But a key point is one of the solutions was to parallel an energy storage system interface with an inverter that could operate asynchronously while the hysteresis curve built up, just as a bridge to allow that CT. And interestingly enough, now GE has a hybrid LM6000 combustion turbine with just enough lithium-ion battery in parallel. They sell it as a spinning reserve, but if you need inrush current, that's also there too. Anyone work on that? Well, Brian, there was some interesting modeling done of that.
Yeah.
Okay, any more questions? Yes, one more.
Brian, so one quick question. When you were developing the models, can you talk more about what format they were in? You mentioned there were different equations. Were they average, linear average, or were they nonlinear average, or did they have switching actions in them?
Yeah, so they are averaged models and they're nonlinear. So the only part we neglect is the switching, which based on the way the controllers that we're using, or most controllers I think are using average mode control. So averaging out the switching anyway seems like a suitable way to move ahead and get something workable. But it is nonlinear, which is why I skipped the algebra, because it's just a bunch of nonlinear algebra that no one wants to look at. But yeah, it's there. No, there's no saturation on that.
Okay, well, if there's no urgent question, let's thank Brian again.
Thanks.